welcome everyone, and I'm going to talk about the extracellular matrix. So the extracellular matrix could be compared, could be seen as analogous to the mortar holding together the bricks, the cells. However, that's a very big simplification. In reality, the extracellular matrix has a lot of functions, including signaling functions that should not be underestimated. The extracellular matrix consists of a core of about 300 proteins, of which there are about 200 glycoproteins. There are a lot of collagens there, elastin there, fibronectin there, fibrillins, and several others. And you have the pericellular matrices, such as the basement membranes that is directly in contact with the cells, and the interstitial matrix. So in this presentation, I will focus mostly on changes in the composition of the extracellular matrix, in fragmentation of the extracellular matrix, and in crosslinking. And I will also, maybe if time permits, briefly touch upon carbamylation. But there is also other things, and I will come briefly to that. Most proteins inside your cell have a very short half-life, ranging from minutes to hours to days at most. Some have very long lifespans. For example, the nuclear pore complex is the core of which, at least in the brain cells, can be in mice conserved for over a year without any turnover. But most of the other proteins inside the cell are very quickly turned over. Extracellular matrix proteins have a very slow turnover. Skin collagen has a turnover of over 14 years, but that's relatively quickly compared to collagen that is in the joints, for example, that it has over 100 years of turnover time. And the collagen is also not, the turnover time is not constant over the age of the person, but increases as you get older. So for example, in young people, intervertebral disc collagen has a turnover rate of 95 years, while in old people it is over 200 years, so very slow. Not only collagen, but also other proteins, such as elastin, have a very long half-life. And in fact, Leslie Roberts, who spoke at the symposium in 2014, has postulated that the aging of elastin is one of the main limits on human lifespan to 100 to 120 years of age. Proteins are under constant attack from intrinsic and extrinsic sources of damage, such as reactive oxygen species, peroxynitrate, isomerization, fragmentation, deamidation, and so on. And this leads them to become damaged old proteins. We start with changes in the ECM composition with age. What you see here is in the left ventricle of the heart, and you see that many of the proteins here are downregulated. Some of them are upregulated, integrins are upregulated, some of the matricellular proteins are upregulated. So there is a vast change in composition. And then we are going to dig a bit deeper. So in collagen, for example, in the bone, we see a decrease with age. We see the same in the skin, a decrease. And you can clearly see that this is the Brunning, a supercentenarian, and you can see just how thin the skin is. You can see all the blood vessels very clearly below it, and that's due to the loss of collagen. But not in all tissues you have a loss of collagen. For example, in the vasculature, you actually have an increase in collagen with age. So the changes is really tissue specific. This is a study that was published a few years ago. And what you see here, this is the DAF2 mutant of C. elegans, which lives long. And then here you have the N2, which is the wild type. And then here what you have is a whole bunch of collagen genes that have been knocked down in the DAF2 mutant, and you see that the lifespan extension of the DAF2 is almost completely reduced to wild type levels. This is at 15 degrees. Here at 20 degrees you don't see a difference, though take into account at 20 degrees you have the DAR induction in the worm. And then here you have dietary restriction, not completely to wild type, but still a significant reduction in lifespan when you knock down collagens. The same happens with mTOR reduction by rapamycin. Also in another mutant of extended lifespan, the reduced germ stem cells, you also see a reduction in lifespan. And finally, if you overexpress collagen in the wild type worm, you see an increase in lifespan. So let's look a bit closer at collagen, and we see that the collagen bundles itself are changing with age. They are getting thicker. You see that very nicely in this histogram here, shorter around 40 nanometers in the young and around 70 nanometers in the old. This is in the heart. In the skin, we see a little bit the opposite. We see that the collagen bundles become thinner. We see that they become fragmented. You see very nicely here just how fragmented they are. And here you see very nicely just how disorganized they become. This is an atomic force microscopy image. And then when we look at the histological coops, here you see some cells that actually are no longer in contact with the extracellular matrix. There is a dead space in between. So what I did here is I took some collagen from the tail of mice, and they dissociated it into pure collagen, and then they had it reformed into a collagen gel in vitro. And so what you see here in the young collagen, the collagen from young animals, it very quickly formed new fibrils, while in the old animals there was a delay, and also there were less fibrils formed. And the fibrils that were formed had a smaller diameter, and also the density of the collagen fibrils was lower. And when they took fibroblasts and they put them into these collagen from young and versus old animals, they found a change in gene expression. Namely, there was more integrins and laminins in the young versus the old collagen, while others, such as, for example, TGF-beta, was increased in the old versus the young. When we look at collagen and we try to digest it in a test tube with various enzymes, collagenase enzymes, we see that with age there is an increase in the time needed to digest it. So this is a log of time versus the age of the donor, and you see a linear curve here. And this has been done in many studies. So why is the collagen becoming ever more difficult to dissolve? Well, because there are crosslinks formed. And here what you see is a study. This one was only focused on using, on looking at enzymatically formed crosslinks, the ones that are normally and necessary for the normal functioning of the collagen. And this was a simulation study, so it's not real data, it's a simulation data. But this is exactly what you will see if you take real data. And what you see here is that this is the curve with no crosslinks, and the more crosslinks, the higher the curve becomes. It's a stress-strain diagram. Stress, so that's the amount of force you take to pull on the collagen fibers, and the strain is the amount that they get longer when you pull on them. And what you see here is basically you need more force to get the same extension. And what you see here is that the more cross-linked the collagen is, the more easily it will snap when you put force on it. Enzymatic cross-linking, there are two main ways. There is the lysine-proline oxidase system, and then there are the tissue transglutaminase system. And we are focusing on the tissue transglutaminase system, mainly TG2. So TG2 activity and expression is increased with age. This was done in a study in 2010. They also found that the amount of these crosslinks, these enzymatic crosslinks, was increased with age. Enzymatic crosslinking is not the only form of crosslinking. You also have age crosslinking, so advanced glycation end products. You have age adducts on top, and you have crosslinks on the bottom. So crosslinks meaning they bind two amino acid residues together. I haven't displayed all the ages on this slide. It's a small selection, of course. Of the crosslinks, these ones are probably the most important in vivo. Very little is known about pentosinane. There are some, such as David Spiegel, who suspect this is actually the main one present in vivo, but it becomes pentosinane upon extraction from the tissue. So that's why you observe pentosidine in your samples, even though it might be pentosinane in vivo. And they all increase with age in the tissue, and they also are increased if you have diabetes. So let's look at the bone. In the bone, we see here this is pentosidine, and you see that there is an increase in pentosidine with age. There's no change in these enzymatic ones in the bone. And what you see here is the failure strength, and the failure strength decreases with age. the elasticity decreases with age, and the work to fracture decreases with age, meaning it becomes stiffer and it's easy to break the collagen in the bone. Not only collagen, but also elastin is degraded with age. Then it forms these elastin-derived peptides which have suggested signaling functions and might actually be toxic. When you take collagen, you can also degrade it by oxidative stress. To my knowledge, I don't know to what extent this happens in vivo. I don't know if this is known, but at least in a test tube, this will happen. So when you take collagen and you incubate it with copper 2+ and hydrogen peroxide, which is a very well-known system to generate oxidative stress, you will see here, this is the collagen bands here, and it's completely lost upon incubation with the copper hydrogen peroxide. But when you add various ROS scavengers, such as here is catalase, you will see it comes back. And then when you take a synthetic peptide, proline glycine 10 times, and you incubate it with copper, there is no change. Hydrogen peroxide, a slight decline, but when you incubate it with both of them, it's a complete loss after just 8 hours of incubation time. In addition to oxidative fragmentation, you also, of course, also have enzymatic fragmentation. We are again looking in the left ventricle of the heart, and you will see there is an upregulation of multiple matrix metalloproteinases. There is also a decrease in some of them. Now, take care, of course, not all of these matrix metalloproteinases are involved in digesting collagen. There are also others that have other functions. And today we are going to talk a lot about senescent cells, and of course senescent cells are known to secrete matrix metalloproteinases. So here you see the mRNA expression level of matrix metalloproteinases is in humans, and you see that they are increased over the non-senescent cells. You also see that here. You see there is also a decline in the tissue inhibitor of matrix metalloproteinases, number 4. And that, of course, means that the MMPs become more active. When we take cells of increased passage number, we also see that they become more phagocytotic towards collagen beads. So you just add the collagen beads, and you see how the collagen beads are taken up by the cells, and this increases with the passage number. What we see in the skin is that a decrease in the production of collagen, a decrease in the production of elastin. Elastin production stops completely very early in life. That a decrease in the production of those and an increase in the fragmentation leads to a thinning of the skin and a loss of the structure of the skin. But there is a little bit of a paradox you might have noticed. On the one hand, I'm saying that collagen with age becomes ever more difficult to digest by collagenase enzymes, and on the other hand, I'm saying that we actually have more fragmentation with age. Well, it could be an error, but I don't think that's the case. It could be a tissue-specific effect, could be, but the main reason I think is what happens is that when the collagen becomes damaged by advanced glycation end products and other modifications, the collagen becomes less able to be digested. So the collagen that is damaged is resistant to being removed, while the newly produced collagen is still susceptible to being degraded by the matrix metalloproteinases, which are increased in expression with old age. So you have an increased disappearance of native collagen and an increased resistance of damaged collagen, leading to an ever more accumulation of damaged collagen. There are many diseases associated with ECM aging. I have listed just a few here. And just let's look at vascular aging. So what we see with vascular aging is that you have dilatation of the aorta, you have an increase in the intima media thickness so that's the wall of the blood vessel. You have increased arterial fibrosis and increased arterial stiffness. And this is caused by changes in the ECM, including an increase in MMPs and a decrease in MMP inhibitors, the TIMPs that I discussed earlier. You have also an increase in elastases, which are the enzymes that degrade elastin, and so leading to elastin fragmentation, and an increase in collagen-elastin ratio. And elastin is 100 to 1,000 times more flexible than collagen, so an increase in collagen will make your blood vessels immediately much more stiffer. But be careful. not only is there a tissue-specific effect, but even within the same tissue, in the aorta, you see that depending on the location you look, there is a difference. There is a major difference. You have increased elastin collagen ratio in the proximal aorta towards the heart, but a decreased elastin collagen ratio in the distal aorta. Aging increases arterial stiffness. That's shown here by 2 different ways to measure it. And we also know that increased aorta stiffness is linked to various diseases. Of course, the main one, cardiovascular mortality, and that's what we see here. Total cardiovascular events is significantly increased in people who have stiffer aortas. Also, total cardiovascular mortality is increased, but even all-cause mortality is increased. So thank you for your attention.